want to talk about viscosity of the Earth's mantle. And I'm going to do that through the context of glacial rebound. So let me give you some background here. About 20,000 years ago, uh, we were a much colder planet, and it's called the last glacial maximum. And we had this continental ice sheet that covered much of Canada. All of this area was under a big ice sheet down to the southern part of the Great Lakes. And it was actually centered, or the thickest part of the ice sheet was centered over what we now know as the Hudson Bay. The Great Lakes are remnants of this ice sheet. They're moraines that were formed during the retreat of the glaciers as they melted. Today we are in a warmer climate, and all that's left of this northern hemisphere continental ice sheet is the Greenland ice sheet right there. And what you can see here is in Hudson Bay, it's below sea level. It's actually not very deep, about 100 meters deep. But during the time of the last glacial maximum, with this big load of ice, continental ice sheet sitting there, it actually depressed the lithosphere, or the Earth's plate, downwards. Not unlike how if you were to sit on your bed, the weight, your own weight, causes a depression. Okay, and that depression was fairly deep, probably about a kilometer or so. But when the ice melted, and it tends to melt much faster than it, or retreats much faster than it takes to build up a large continental ice sheet. It melts at a rate much faster than the plate or the lithosphere can actually respond. So in the analogy of your bed, if you were to get off of your bed, that depression would flatten out, would come right back up, and it'd be flat again. But there's a little bit of a response time, okay, for that to happen. So for some amount of time, there will still be a depression, in this case, the Hudson Bay, and it gets filled in with water. Now, this depression, or the relaxation of this depression, is what we call glacial rebound. And it's controlled by the rate at which the mantle can actually flow back in underneath to fill up the depression. And that takes some time because, as you know, the mantle viscosity is very slow. And the fact that this hasn't, although it's very shallow now and almost done, it's not complete. But we can say the time scale for this relaxation is going to be on the order of 10,000, 20,000 years. If you don't believe me, the evidence is shown here. You can go on, I'm zooming into the edge of Hudson Bay, and you can see these linear or arcuate structures. And these are old shorelines, beaches. They each were at sea level, but as the crust relaxes and rebounds, each progressive shoreline gets elevated upwards, because going back to where it used to be before there was an ice sheet that had pushed it down, and gets stranded upwards. And you can actually date all of these shorelines, and since you know the elevation of those, you can actually put a constraint on the rate at which the lithosphere and the mantle beneath are responding to this sudden unloading of the ice sheets. So that's what we're going to do. We're going to go from there. So let me just going to make a plot of the temperature of our surface Earth from paleoclimate studies, like ice core studies, and this is time, and this is today, and this is, say, 20 kiloyears, 1,000 years before, and what we see is something that looks like this. Okay, it's not exactly accurate the way I drew it. This is about 150 kiloyears And what it's showing you here is that, of course, if you're cold down here, these are the ice ages, and these are the periods where you don't have such large continental ice sheets when you're warm. Okay, up here, that's where we are right now. Just as an aside, um, if you were to superimpose anthropogenic climate change on this, it's actually taking us up here away from this background trend. But I don't want to talk about that here. But what I want to show you here is the asymmetry of the temperature record. CO2, PCO2 is also asymmetric. And what happens is to go into an ice age, to build up these ice sheets, that's going this way, right? As you get colder, it actually takes a long time to do so, to build up an ice sheet. But to get rid of an ice sheet, it actually doesn't take that much time. It goes very quickly. And I obviously didn't do this to scale, but it's fast. And it's fast enough that when you melt all the ice over Hudson Bay, the mantle has not been able to respond instantly. And so there's essentially a hole in the ground that is isostatically uncompensated, and therefore it wants to rebound and fill up. Okay, so let's go into this a little bit in more depth. And what I'm going to do is try to keep it simple. So what we have is during the time when you have an ice sheet, okay, you will have continental ice sheet like this, and this is the lithosphere, which is mostly made out of the peridotite or the mantle, and this is so this is the lithosphere, and this is, we can call it the asthenosphere. Okay, that's the part that's below the lithosphere or the thermal boundary layer. It's the hot part. The lithosphere, it behaves as an elastic plate, and the load of the ice right here causes a depression. And because it is built up very slowly, we can assume that it's in isostatic equilibrium. Now, what does that mean, right? Well, first thing I'm going to do is describe the ice sheet here with the thickness h, okay? And we're going to simplify this. I'm going to assume that the lithosphere is the same thickness everywhere, and I'm going to think of it as a background and just subtract it out. And so our idealized ice sheet thing would look like this. Just keep it simple. This is my ice sheet. And now this whole thing is the asthenosphere. And we can think of this as the ice sheet thickness is h. This right here would be the elevation of the ice sheet sitting above sea level. And this right here would be the root or the depression, okay? Call that R, okay? I didn't draw it to scale because the ice is so low density, the amount sticking out is much more than the amount sticking beneath. But this HR would be equivalent to this or this as well, okay? That's the same thing. Now, when something is in isostatic equilibrium, what it means is at the bottom of this body, there are no lateral pressure gradients, which is to say that the pressure here underneath the ice sheet is the same at the same level within the Earth. They're equal. Above that, they actually aren't equal, but down here, they're equal. So we can write a simple equation where I'm going to call the density of the ice rho I. So rho I times G times capital H would be the pressure at this point, okay? And that will equal the pressure in the mantle at the same level right here. And that would be, we'll call rho mantle times the gravitational acceleration times HR, okay? We don't account for the atmosphere because the density is effectively 0. And recognizing that H is equal to HE plus HR, right? we can write this equation where rho I and the g's will cancel. HE plus HR equals rho M and HR. And we can rearrange all of this to get HE, the elevation, is the density of ice over the density of the mantle minus the density of ice is equal to HR, right? So that's the density contrast in parentheses, or you can say HE is equal to a delta rho over rho I times HR. Now, to give you some context, we think that if you look at Antarctica as an example, and maybe in the last glacial maximum there was more ice, that the elevation of ice might have been about 3 kilometers. Right? And the density of ice is approximately 10 to the 3 kilograms per meter cubed. And the density of the mantle is 3,300, but I'm just going to say 3 times 10 to the third kilograms per meter cubed. So if I plug numbers into here, that would be delta rho 3,000 minus 1,000 is 2,000. And this would be initial density of ice, 2, and HR. This then here equals 3 kilometers. So what we end up getting is that HR, the root thickness, would be about 1.5 kilometers. So the total thickness of ice would be about 1.5 plus 3, or 4.5 kilometers. Okay, so the 4 kilometer thick, 4.5 kilometer thick ice sheet will have 3 kilometers sticking above sea level and 1.5 below sea level. Okay, so actually the way I drew it is not really to scale. It should look something more like this. Okay, that's the sort of depression. Okay, so now what happens if we suddenly melt the ice and it disappears? Well, what we do is we take that same diagram that we had and we just magically disappear the ice. And now you have a little void here, and now we're interested in the pressure here and the pressure at this spot, the 1. And we know that this pressure is going to be greater than this, so it's going to drive a pressure gradient here that will actually cause flow to go up. Okay. Now, what we're going to do, instead of assuming it's all air, we'll just say it fills up with water. Okay. But it fills up so fast that it's not isostatic compensated, and eventually this thing's going to rebound and the water will flow out there. So if we were to calculate the pressure at this point, then, and I'm going to call this HR now. One thing I forgot to mention is I'm going to call the radius of this ice sheet as L. That would be L, right? L. This will become important later. And so at P1, it's rho of the water, G, HR. And then at P2 is rho mantle, G, HR. Such that the total pressure difference is now going to be delta rho. In this case is water and mantle, but it's this water is almost the same as ice, so I don't worry about it. GHR. Okay. So what if I draw this again, cleaned up version? There is now a pressure gradient here. The highest pressure is this point right here, and that's going to be approximately delta rho GHR. Okay. And if you saw my talk on strain rate and how that relates to stress, we can think of this as like a flow, Poisson flow of mantle rising upwards, and this we can think of as a shear stress acting over a distance of approximately L, which is the radius of this depression, okay? So this delta rho g h r, that's the pressure gradient, is going to be met by a viscous resistance or a frictional force of negative this quantity, the viscosity times the strain rate. Okay, you're going to have to look at my previous talk to know what the strain rate is. Anyway, this is a constituent law, Newtonian fluid. The negative sign is there because my pressure gradient is positive, and the strain rate, of course, this would be negative there. And this equals negative eta, and epsilon dot is essentially, you can think of it as the velocity of this rebound, right? Divided by L, okay? So I could draw a velocity field, and this would be V, and this distance L. Okay, that's the strain rate, and then this the shear strain right there. And velocity, of course, is can be approximately dhr dt over L, right? You see that? Okay. I can then take delta rho g L eta negative this, and take the dt to this side. This becomes dh r over hr. Okay, so interesting equation, because anytime you see a differential, a fractional differential like this, dy over y, you'll get an exponential relationship. So this, if you were to solve this, would show you how HR, and I would define HR here as the depth of this depression at the center, is going to be something like this. The initial depth exponent to the negative delta rho g L eta times T. Okay, so HR is going to, or the depth of depression is going to get smaller and smaller time, but it's going to decay exponentially. Okay? And this quantity right here, delta rho GL, if you flipped it over, has units of time. So eta over delta rho GL has units of time, and we'll call that a characteristic time, and that's the relaxation time. Okay, and we know this to be about 10, 20,000 years. And if you know that, and you know these other quantities, then that, in theory, puts a constraint on viscosity. So we can rearrange this equation. Eta is equal to, or approximately equal to, my relaxation time, delta rho g L. Okay. And if we start to put some numbers in here, I would put, and you can do that as an exercise yourself. My relaxation time might be 10 to the 4 years, okay, 10,000 years based on the geologic observations. Delta rho is between the mantle and water, so 3,000 minus 1,000, so that's about 2 times 10 to the 3 kilograms per meter cubed. G is 10 meters per second squared. And L, the length scale of that ice sheet, or the radius, about 1,000. It could be 2,000, but I'm not worried about. I'm only worried about orders of magnitude. So let's call L. This is G. This is L. Is about 10 to the 3 kilometers. Okay. Now you got to convert all these to the right units. That's delta rho, and this is tau star. You put all that in. What you end up getting is the viscosity of the mantle that resists the immediate relaxation here is going to be approximately 10 to the 21 Pascal seconds. Okay. That's how, or one of the ways we get the viscosity of the mantle. Of course, if you really want to do it right, you have to, it's much more sophisticated calculation here, and you have to consider there's a depth-dependent viscosity. But this gives you the essence of what glacial rebound studies are trying to do. Now, 10 to 21 Pascal seconds, of course, is much higher than that of basaltic lava, which is about 1 Pascal a second, or water, which is even less. So this is a really, really viscous substance that just takes a long time to move, to flow. Some of you may be more accustomed to a lower viscosity for the mantle, which is what I assumed in the previous talk, of 10 to the 18 Pascal a second. And that's what we think the viscosity is in the flowing part there, the asthenosphere. And the reason why we probably get a higher viscosity here, or the response time is slow, is because we're sitting on the cold craton of North America. And viscosity depends on temperature exponentially. So the colder it is, the much more viscous it is. So we have a thick, 200 kilometer thick lithosphere there. And so that is controlling some of this rebound, not just the asthenosphere here. This is why we get a higher viscosity here. Okay. That should be enough.